Okay, so in the next 40 minutes, we'll just consider one problem as an illustration of the subtlety and also some possibility of interactive proof. So schematically, interactive proof involving two players, the prover and verifier. And each player has their own so-called private space. You know, what happened in their mind, stay in their mind. So they can keep certain things private. Particularly, it means that they are able to use certain randomness privately, right? And this, in many ways, can be considered as some kind of challenge, that you want to have unpredictable challenge. And that comes from this notion of randomization. Okay. And for now, let's assume that the verifier is just a polynomial time machine. For now, let's just stay true with the NP, because that's closer to what we know about complexity in the first place. So let's just assume this is a polynomial time machine. And the prover itself, let's assume, is an all-powerful machine, just like in all days of NP, right? If it exists, it can offer you a solution. Right? So this prover is powerful. It can take an exponential amount of time to compute, and because in its world the time flies fast, so that's why it can do a lot of computation in short time. And so we can talk about a particular language, right? Just like 3-set is a language. 3-set means that the type of formulas that is satisfiable, right? So we're considering for now a restricted problem of such a decision problem. So usually we call decision. Remember, decision problem is just I try to give you a syntactic description of a language. I give you another string. I ask you whether it's part of the language. Right? So if I define language to be all satisfiable expressions, I give you expression, you need to decide what is satisfiable. Right? If my language is all graph that can be colored by 4 colors, then the decision problem is if I give you a graph, I want you to know the answer whether you can color it by 4 colors. Okay? So the problem that we are going to consider is graph. Let me put a noun into the parentheses. Graph isomorphism. So graph isomorphism problem, in the simplest way, defines the following: that I give you 2 graphs, input G and H. So they are basically vertex and edges, right? So here in graph isomorphism, I assume the 2 sets of vertex are the same. So which means I can remove the index. So they are on the same set of vertex. And when we say G is isomorphic to H, if there exists a permutation phi such let's use pi. I'm going to use phi again, such that so this permutations go from V to V. So it's permutation of vertices, such that UV belong to E of G if and only if pi U pi V belong to H. Right? So this is called graph isomorphism. That is there's a renaming or relabeling of the vertices that this graph are the same. Right. So for example, the following graph 1, 2, 3, 4 is isomorphic to this graph. So these two graphs, even though in the labeled version they are different, but these two graphs are the same graph. You can just look at this. So essentially, the symmetry indicating that if you map 2 to 1, 4 to 3, and 1 and 2 respectively to 4 and 2, you actually get the same graph. Right. So this is called graph isomorphism. Graph non-isomorphism clearly means is to indicating whether two graphs are not isomorphic. Right. So which means that the language which we define will be the input will be just G and H, such that G is isomorphic to H. So this is called graph isomorphism. And the complement of this L bar is graph non-isomorphic. Right? That is, they do not have any way to map them to be the same. Okay. So this is one of the fascinating problems, because often in practice people need to determine whether a particular task graph or particular situation are identical, right? Because it could be generated by different people. That's why they put a different name on the nodes, label on the nodes, but they want to determine whether intrinsically they are same, right? And it's related with another problem called subgraph isomorphism, which are, I think, often referred if you look at the proposals in Homeland Security. Right? So subgraph isomorphism is one of them more appropriately referred when people talk about doing network analysis. You try to recognize certain patterns so that they can identify certain aspect of interaction and activity. Right? So that problem is slightly different from this one, but this particular one is just asking for two graphs, whether they are identical or not after permutation. Okay? So this problem has been there for a long time. People have been thought about this, for probably 100 years. And complexity theoretical study really quickly put this into a prominent place, because for a long time people don't know how to solve this in polynomial time. Okay, and then the NP P theory come out, NP completeness come out, and people couldn't prove whether it's NP complete or not for a very long time. This many people attempt to prove graph isomorphism is NP complete. They fail, and eventually people has evidence to prove that it's highly unlikely it's NP complete. To such proof, it's highly unlikely it's NP complete. Okay, and still for a long time there's no polynomial time solution, except for a few simpler cases. For example, it is polynomial time decidable if two trees are isomorphic. That's a non-trivial result actually, if you think about it. I give you two trees, I ask you whether they're isomorphic, and it turns out that to be polynomial time decidable. And it's even a probably bigger result in 70s is that one can decide if two planar graphs are isomorphic to each other. If two planar graphs, that's actually, you can think about it, much harder task. But there are polynomial time procedures, and to decide whether two planar graphs are isomorphic to each other. And those results eventually extended, cumulated to an early result by Jin Lux. He's a professor in, I think, Oregon right now, University of Oregon. And so Jin Lux proved the following result, which essentially set the stage for many of future work. He proved that if both G and H has a constant degree, namely you don't have vertex has a larger degree. If G and H has a constant degree, then Jin-Lux find a group theoretical approach to show that such graph can be decided in polynomial time. But polynomial will be has exponent of the degree. Polynomial has exponent of the degree. Right? So that's one of the huge breakthrough in 80s. That people began to understand the power of algebraic computation in graph theory. To prove that graph isomorphism for constant degree graph or some variation of constant degree graph can be tested in polynomial time. Okay? But still for a very long time, the best result before this year, I think before last year, has been graph isomorphism can be decided in 2 to the square root of n time. It's exponential, but clearly intuitively winding is not NP complete. Right? Because NP complete, people still don't know how to bring them down below 2 to the n, exponential in n, or some constant to the n. And this it has a solution of 2 to the n. It went through few reduction techniques. Some are elementary, some are group theoretical. So it's able to bring down this. And some basic other families gradually go down until very recently last year, by Lati Bai, who is one of the leading experts in computational group theory and graph isomorphism. He proved that the graph isomorphism can be tested into the order of a polylog. So essentially, this is closer to polynomial time as possible. But still, this is the current baseline right now. Okay, it's a fascinating problem. And I spent some time in graph isomorphism too, but unfortunately my group theory is totally untrained. So after a while I really realized my limitations, and I began to move on to some other problems as well. Right? So it's sometimes rely on sophisticated mathematical build-up. And so Lassi Bai made the first advance in interactive proof. Okay? So the same Bai. And also he used graph isomorphism as an example. So this is a man who is really remarkable. That he has been pounding graph isomorphism basically for 40 plus years. And not only he's pounding on graph isomorphism, he's able to use graph isomorphism continuously as a benchmark example to create many new concepts, including interactive proof. Right? So this is truly remarkable. Just not just solve a problem for solving the problem's sake. He's able to use this problem to continue to see many brilliant new concepts. Right? One of which is interactive proof. So he won Knuth Prize a few years ago, and I was fortunately one of his nominators. That's why I read very heavily about what he has done in life, and greatly appreciate how graph isomorphism is almost like a continuous thread, that each of the great inventions he did has some image of this graph isomorphism problem, which is just truly remarkable. Okay, just like crypto, right? It has a common thread of pseudo-randomness and encryption. How do you encrypt, right? So this fundamental notion is driving the field. Okay, so. But still, nevertheless, nobody knows how to solve graph non-isomorphism or isomorphism in polynomial time. Which actually, the following problem continue to be open, where the graph, I mean write down Gi, belong to co-NP. Which means that where the graph non-isomorphism has an NP proof. So this actually has been a hunting problem also for the field. I mean, of course, if this all push into polynomial time, then everyone has polynomial proof. Right? But still, even though this push is so low, it's still a hunting problem where the graph non-isomorphism has a NP proof. Which means that a decisive one round perfect completeness and perfect soundness proof. Right? So this is where Nazi, bye-bye, is really remarkable. He actually changed the notion of the proof system and allow you to use randomization and approximation. Right? So here is his first result. His first result is following. So this really opened up the study. He proved graph non-isomorphism can be proved using an interactive proof, where the verifier is just polynomial time machine. So this is a major work that initiated a remarkable follow-up. It comes from this very simple example. Graph non-isomorphism, like I will call GI. Let me just non-GI belong to interactive proof. Right, so this is from last. Right? And this protocol is utterly simple. It only taking me probably a few minutes just to explain. It's utterly simple. In some sense, it's really insight to see this thing, rather than actually conduct this particular proof. Okay, it's really insight to formulate this thing. Okay, so this, in my mind, is a sort of computer science, theoretical computer science at its best. It's really you absolutely have the instinct to see a phenomenon rather than someone else formulate. You say here is a proof. Right? This absolutely comes from the creativity. Okay, so here is the result of Nazi bye-bye. He said, how do we do an interactive proof of something non-isomorphic? You know, you can easily do interactive proof for something isomorphic, because every NP problem has such a proof. Right? You can see the fundamental difference between when you negate it. For example, can we prove that 3 set has no solution? It's different from proof 3 set has solution. No solution, you have to rule out all possible solutions. Right? So this, which Lassie said, is where randomization actually helped. Right? So here is his protocol. You have your P, you have your V, and here your graph showed up, G and H. Remember, we want a completeness or soundness. Completeness should say, if we want 100% completeness, to say, after the interaction, if G and H are non-isomorphic, the verifier has to say yes, to accept. If they're isomorphic, perfectness is verifier will say no. But if you approximate it, it means verifier will say no with high probability. Right, so I will rewrite that after I did this proof. Okay? So here is Bai's proof. He said, since they all know G and H, this is what the verifier will do. So this is called challenge and response. Right, so this is what I call the PhD qualifying exam. So he write down just a protocol for PhD qualifying exam, nothing more than that. Okay? So he said, the verifiers are the professors. The provers are students. They need to pass the exam. And the student was assigned a task to study graph isomorphism, came back to say, I'm expert. Right? So it needs to convince the professor that he can pass the test. So as a result, the department committee came up with 2 graphs and asked the student to identify they are not isomorphic. Right? If the student can identify that, then the professor will say, good students, you passed, you can continue on with your study. Right? And so what does the professor do? The professor, in this particular case, want to just stir the question up a little bit. He just say, randomly. So whenever I write down here, I mean locally, which means the student couldn't see. Right? It's in the mind of the professor. Right? He just randomly choose prime from V to V. Randomly choose pi to V to V. And second, choose I from. So let me change this to be G0 and G1. Right. So let me just give a simple index. So you can see this protocol is crypto protocol. There's nothing different from usually when we do. This is what I call Turing test. Remember I said the wine tasting? There's not much different from this schema. Then, after this, it will compute the graph. And then it just sends G tilde here. So it did this in private, randomly choose a permutation, randomly choose a graph, permute it, and then just stuck the graph here. Ask the student to say, the question is, so the challenge, is G tilde isomorphic to G0 or isomorphic to G1? That's the question. That's called challenge. The challenge is that it produces a random graph from the input and challenge the student to say isomorphic to G0 or isomorphic to G1. As you expected, right? We see this protocol. So that's why hindsight, this is just simple, but it's just brilliant, right? Well, I wish we was in this historic moment to see this, right? And then the prover will return an I prime. That's your Turing test. That's your wine tasting. Right? You have these two wines. The student declare is expert to tell the difference. So this is basically the same thing, right? The professor take a random wine and put in the glass and just randomly squirt the wine around and put the glass out. And ask the student to answer, right? So if I prime is equal to I, except if I prime is not equal to I, this is just our crypto test. We have been doing this test for the whole semester, if you think about it, right? So that's why you can see when the field advances to a certain degree, when certain things become standard, then people can use this in their research, just like that. Right? Because this suddenly test was formalized in the entire field. Many people study this thing, right? So it's no different from this thing, right? So by just analyze what is the quality of this schema, right? To make a statement. So here is what he realized. It's just absolutely simple. For the completeness, if the graph is non-isomorphic, can the student convince professor? Always. Students are all powerful. Professors are lowly polynomial time machine right now. Powerful students, right? If you have powerful students, if G and H are non-isomorphic, can students solve this problem always without being rejected? Yes. Right? Because when G prime came, it can only be isomorphic to one of them. Since the students are so capable, as most of our students are, that the student can just take a glance to say, that's G0, that's G1, right? It's just a mind test, right? The student has perfect knowledge of the graph, perfect knowledge of Y, perfect knowledge of knowledge and data. So clearly, this is 100% complete, right? It's 100% complete proof system, right? If a student want to convince professor, powerful student should pass the test if the graph are not isomorphic. Agree? Because powerful student can always tell the difference between this graph and any of the two, so it will make an equivalence. Right. So how about soundness? If the graphs are isomorphic to each other, what is the probability a student can pass the test? If the two graphs are isomorphic to each other, what is the probability a student can pass the test? The student needs to pass the test to declare it's not. The student wanted to declare it's not isomorphic, right? The student's job is to convince the professor it's not isomorphic, right? The student's job is not to convince the professor's truth. He's just trying to convince. He can only pass when you say not isomorphic, right? So this is just our traditional wine test. If I ask you whether two wines, the same wine, are different, what's your chance to tell? If I randomly give one of the two wines to the unlabeled one, 50%. There's nothing you can do, right? The student, if facing the same graph, the challenge comes to them just the same challenge, right? So that's why if G0 is isomorphic to G1, the student at best convince professor to accept. With probability 50%. So if the professor asks the student twice, what does this probability become? 25%. Right? If asked 3 times, it becomes 12.5%. Right? So you can see the professor can just ask a few around to drop this probability as close to. Right? So if you really also think about this, this can be loosely also viewed as a so-called identification schema. Right? The student is an expert of graph non-isomorphism. That's why he tried to use this. We set up professor as a bank of 2 complex graphs, different. The student can always tell the difference between the which one. Then he can log in on the machine. But a student don't know how to solve this problem, cannot do better than just guessing. Right? So this is the similar argument. Right? So this is what Viterbi realized. He basically said, if you look, the power came from randomization and a small realization of the soundness. Right? If you allow bank to take insurance against a faulty log onto your computer, then this complex problem can be used as identification. Because, you know, a faulty person might have a chance to log onto the computer to get your money. But that happens with exceptionally small probability if we ask a few more rounds. Right? Because in each round, the chance to pass is 50%. So if I ask a K round, the chance to pass when you don't have knowledge is less than 1/2 to the K. Right. So this is one of the first so-called interactive proof of a problem that is not known to be in NP. So this is in Viterbi's view, he somehow extended the NP. He said that there's a language class that are more subject to such tests than just the straightforward NP test. Namely, you give me answers, you have to be perfect. Everything is deterministic. Once randomization is thrown in, once you allow the verifier to take insurance, then he put some other problem which is not known in NP into somehow is schematically acceptable, right? So that's why Viterbi asked complexity theoretically, is ID. What is power? Far more powerful. Than NP. So that's basically his main theme to study at a junction, right? Is interaction greatly improve our chance to design such testing system if we allow the verifier to take insurance. Right, so that is the complexity theoretic question. This is a complexity theoretical question. Right. If you allow interaction, how much more can you prove as a system? Right? It's a proving system. Right? But this fundamentally introduces the notion of challenge and response as a possible mechanism to formalize them as identification and mathematical proof. Okay? So next time, what we are going to do is to put notion of knowledge in such a thing. So that's basically give a rise to our discussion of zero knowledge proof. So next time I will attempt to formulate this notion of knowledge. Since I have 5 more minutes, so let me just give you a small dose of just, I think continuously, I think it's an important philosophical question. That is, humans are limited. How do humans participate security system? I think it's a beautiful question, right? It's just, this is really what we are facing, right? You can have theories so advancedly developed, people even have zero knowledge proof, right? But human can, how much of this we can do? It's just not much, right? Because humans are just not able to manipulate such a thing, right? Including trained people, right? So that's why you can see the gap fundamental from theory and practice. But on the other hand, sometimes philosophical scheme expand in practice. So for example, one of the following family of schema was produced to enhance password that instead use this kind of $60 device. Right? So I just give you one possible such a schema. So if you allow challenge and response, then you can make this fact that communication between user and ATM machine is totally insecure to at least make it go away a little bit. It's not perfectly go away, but you can. So imagine the following schema, that instead of having you just password, instead of having just password, how many we said? 4 digits, right? We said 4 digits or 6 digits, right? Imagine that all your secrets are in pairs. Suppose all your secrets are in pairs. Let's just say each has 4 digits. X1, Y1, X2, Y2. Suppose you begin to collect some of your password, right? So if you have a lot of these secret pairs, then intuitively you can design the following challenge and response login system. That is following. When you try to log on to the ATM machine, you put in your card. Right? Then the machine on the panel will just produce a bunch of random numbers. Okay? So then your job is to retype a bunch of random numbers with the following property. Suppose somewhere X is embedded into the system, you are allowed to flip them into the Y's. One of the Y's. And the rest of the time you just type random things. So that is another possibility to enhance password. That is, imagine you have 10 passwords, and every time when bank showed up, one of your passwords is embedded in one of the first part is is embedded in a bunch of random string, which can be much longer. So since you don't need to remember the random strings, and you only need to scan the random string to identify a pattern of your left-hand side pattern, then in your mind you convert them back into the matching password, and then you just type the rest as random things. Right? So this, in many ways, is one of the reasonably close replica of interactive proof that directly just allow human to use some limited password pair. Right? And one can actually study such a thing mathematically on how many rounds you need to do statistical tests in order to identify a pair. Right? So that clearly depends on how long is everything. And I think the early study is still a little bit lacking. They said in order to keep the machine running for a few months, and at that time we still need to remember 20 digits per code. So I don't know what our ability to remember 20 digits, but still that's a progress. It's no longer. So if every few months you're able to remember mentally certain random pair of the patterns, you have ability to spot them very quickly on the screen, and you have ability to type in the rest thing randomly, then this thing will survive for a while. The only difficulty is when human type a random thing filled with their patterns, the speed of the test may change. It could be they type random thing with one speed, and once they enter their pattern, they either slow down or speed up, most likely slow down. Right? So then if somebody else they're watching them, they actually may know where they actually. Right? So that's why statistical attack is a very dangerous attack, right? It doesn't have to be about digital. It could be some other, what I call side channel attack. Right? If you allow to use side channel attack, many other things can break. Right? But still mathematically, imagine a human can pass, people can train to pass what, lie detectors. Essentially, they try to regulate the response as uniform as possible. Maybe the future generation of human can quickly flip random strings, and even with the pattern, they can just evolve this uniform speed type through. Then some of those things can actually allow human to answer this challenge and response question. So which means that bank always asks random questions, right? If you look at today on internet, when you try to create an account, they usually ask you to recognize some characters, right? Those are challenging and response. As you can see, right? It came very similar to such a schema. Right? How many times you actually look at the pattern, you actually say, gosh, that's actually not easy. Sometimes they, right? Because they don't want the machine generating the stuff to create a lot of count, right? So that's often they do this. And that schema is not that far away from this, you can see, right? And it came schematically from the notion of interactive proof, right? This fundamental notion of challenge and response in interaction may create a schema that is more palatable to practical implementations, right? But still, the bottleneck is us. It's a remarkably bottleneck, right? Because we just couldn't manipulate much, right? We just only remember small fraction things, and we can't consistently conduct certain things, right? So you can relax such a schema. You don't have to perfectly fill in. You can have 90% fill in. That's give randomness certain thing. But oral schema still I think is far away from practice, because if mathematically evaluating, you want it lasts for a few months, then you do need much bigger code. But on the other hand, when you log on to ATM machine, you don't always log at the same place, right? You go to different machines, so they may not see enough sample. So maybe this you can still 5 to 6 digits pairs. It may protect you for a while, because when people see, they only see one sample of you doing. Then next day you're in different ATM machine and you're in different countries, right? So, but tomorrow, next time, we'll focus on zero knowledge. And this allows us to channel everything we define to think not just encryption, but think about computation. Right? So I think that's, I find is really the advance of modern cryptography. Oh, any of you who can move up to which date opened up the 14. So if any of you can move up to 14, let me know. And particularly, I think so far we have 3 scheduled in the last 2 sessions, right? Because if we're not scheduled in, so 14 now we only have 1. So if anyone want to move in there,